Hello, I'm Chris Tunsley, Director of Product Marketing at Graphcore. During this presentation, I will talk about our unique technology and how it has been designed for machine intelligence performance and efficient scalability. We live in a world where AI or machine intelligence is increasingly being used to solve complex problems across many market verticals. With the push for ever-improving capability and accuracy, AI model sizes are increasing rapidly, driving the need for highly efficient, highly scalable systems. In this presentation, we will take a look at our IPU processor and how it is different. We will look at how scalability for AI is designed in throughout Graphcore's technology. We'll also look at the target markets for IPU with real-world use cases to show how the IPU is enabling innovation. First, a few words to introduce Graphcore. We have global coverage with our headquarters in the UK. Our main design centre is in Bristol, and we have two other UK R&D centres in London and in Cambridge. We have a second major design centre in Oslo in Norway, and this is where all of our system-level products are designed and developed. Elsewhere in mainland Europe, we have sales offices in Paris, Munich, and Gdansk. In Asia, we have sales and support offices in Seoul, Korea, and Tokyo, Japan. In China, we have offices in Beijing, Shanghai, and Shenzhen. We have an operations team in Taipei because our silicon devices and platforms are manufactured in Taiwan. And we have offices in the US covering all the US time zones in New York, Austin, and Seattle, with our US headquarters in Palo Alto. Put simply, Graphcore develops processors specifically designed for AI and machine learning workloads. We provide hardware technology as the IPU processor and software as the popular software and development tools as part of a complete solution to enable innovators to solve current and future machine learning problems. Last year, we announced our second-generation IPU processor, the Mark II. This is delivered in the IPU M2000 product and IPU Pod rack-scale products, which provide scalable deployment so users can start small and scale up to thousands of IPUs. But to help set the scene, I'll highlight some of the trends in the market and the drivers and motivation for our IPU products. We are seeing an ongoing trend towards huge growth in model size and complexity, as you can see from the models highlighted on this chart. One of the key drivers for this growth is the pursuit of increasing accuracy, which is so important to organizations using these models. So to achieve this drive to increased accuracy, there's a natural trend towards bigger models. This means more parameters or weights to encompass the increased learning. This in turn means more compute, which translates to more power, which ultimately becomes unsustainable. With these kind of model trends, there's a need for models that don't just throw more dense computations at the problem. There's a huge amount of interest in model efficiency, getting more bang for your buck in terms of parameters or weights. The challenge is that many of these new efficient models don't necessarily map well to legacy processor architectures. So a new approach is required to enable people to explore areas and research directions that they haven't been able to explore before. As no single processor can fit a model with billions or trillions of parameters, we need a very efficient scale-out fabric optimized for the needs of machine intelligence. One thing that's important to understand about machine intelligence, or AI, is that it represents a completely new workload, requiring different attributes in an AI processor. With machine intelligence workloads, we are typically dealing with massive parallelism, requiring massively parallel processing capabilities. The data structures are fundamentally sparse. Not all parameters connect to everything else, and problems are very high dimensional, yet we are mapping these to a memory structure that has just one dimension. We therefore need a processor which does not rely on dense, contiguous data structures for efficient implementation. Compute for machine learning is also low precision. It's the ensemble of all these low precision operations that makes the highly precise output we are looking for from our model. There's a lot of reuse from the model parameters once loaded into memory for convolutions and recurrence. Fundamentally, compute graphs are static. Like in a brain, you don't rewire the neurons for every new task. Taking advantage of this static nature, we can build tools which map our complex graph structures onto the complex processor architectures. So if we find a way to leverage those in the hardware we use, we would expect to achieve a major performance and efficiency improvement. Let's consider the processors that are predominantly being used for machine learning today. We're familiar with CPUs. They were developed for scalar processing and running general-purpose applications. The GPU was designed for graphics or vector processing, and in some cases have had some additional cores to help address some of the workloads for machine learning. But essentially, these are processors that were designed for a different purpose. By contrast, the Intelligence Processing Unit, the IPU, has been developed from the ground up specifically for machine intelligence workloads and to enable a more flexible approach to these kind of models. The IPU architecture provides lots of parallel cores, which means you can have different parts of a model that are doing different things to different data all at the same time. This is a capability that cannot be efficiently implemented on legacy architectures like a GPU. This fundamentally different architecture enables huge benefits for these new types of machine learning and many other computational workloads. And it's not just us that think AI needs a different kind of processor. A few years ago, Geoff Hinton, winner of the Turing Award, together with Yoshua Bengio and Yann LeCun, for their work on deep learning, and sometimes referred to as one of the godfathers of AI, was being interviewed by Wired. During the interview, he was asked, how might we build machine learning systems that function more like a brain? To which he replied, I think we need to move toward a different kind of computer. Fortunately, I have one here. And he reaches into his wallet, pulls out a large, shiny silicon chip, the IPU processor. So how is the IPU different? It's in two key aspects, the level of parallelism and how it maximizes the memory access. Let's look at both of these topics of this generalized comparison to help illustrate. In the case of parallelism, as mentioned before, the CPU is a processor that was designed for scalar processing and running general-purpose applications. They typically have a comparatively low number of cores. The GPU was designed for graphics processing, which has a SIMD, SIMT architecture, which requires putting as much data as possible into contiguous vectors to make the most efficient use of those instructions. So it is designed to work with large blocks of dense contiguous data. The IPU, however, is a massively parallel MIMD architecture, multiple instruction, multiple data. It can also be described as having a fine-grained architecture, which is needed to address the growing trend towards more efficient AI models. And now looking at the memory access, it really comes down to where the model and its associated data reside. This is a very memory-intense activity, so the performance is heavily influenced by the memory bandwidth available. In the case of CPUs, memory is typically off-chip, which can be very limiting in terms of memory bandwidth. In the case of GPUs, the use of high bandwidth memory, or HBM2, within the package can improve the memory bandwidth by a factor of maybe 5x. On the IPU, the model and data is held in tightly coupled SRAM right next to the compute. This gives us a huge step up in memory bandwidth, which translates directly to performance. And here we show our Mark II IPU processor, the GC200, in a little more detail. The IPU compute is provided by 1,472 fully programmable IPU compute tiles, each of which has 624 kilobytes of tightly coupled, locally distributed SRAM, which means each IPU has 900 megabytes of in-processor memory. That's almost a gigabyte of memory available on each IPU processor, making data available at ultra-fast memory bandwidth of 47.5 terabytes per second. Our IPU machine, the IPU M2000, is our building block for scalable IPU machine intelligence systems. It contains 4 Mark II IPU devices connected by an IPU link. Up to 16 of these IPU M2000s can be stacked in an industry-standard rack into an IPU Pod 64. This provides the core building block for further scale-out, allowing potentially up to 64,000 IPUs to be supported, delivering up to 16 exaflops of AI compute. Our scaling story starts with the scaling within the IPU processor itself. As we have seen, the IPU is made up of many duplicated processors, which we call IPU tiles. The replication of IPU tiles in this way means we have parallel scaling of almost 1,500 independent processors within each IPU and high-speed communication between them with IPU exchange. It's driven by compiler support in software and is fully timing deterministic in its execution. Along with scaling on the IPU device, we also support scaling across IPU devices. This allows us to introduce model and data parallel constructs to IPU applications. IPU Link is our technology we use to connect IPUs together. This functionality allows us to build IPU applications at massive scale, Again, this is driven by support in our software stack. And here we see a number of vertical markets that utilize machine intelligence workloads that are proving to be highly suited to the IPU. Data center consumer internet uses machine learning extensively, and the IPU is being used for a variety of search and recommendation use cases. In the field of research and higher education, we have a number of universities and institutions that are already seeing huge performance benefits in their simulation and research work. And the IPU is being used in multiple healthcare applications, such as medical diagnosis and drug discovery. Finance is also a market where the IPU is enabling innovation in many fields, such as trading, forecasting, and insurance. And here we have a real-world example in the finance industry where IPUs are enabling new areas of innovation. Researchers at the Oxford Mann Institute of Quantitative Finance have used the IPU to dramatically accelerate the training of advanced price prediction models using multi-horizon models and techniques, which don't work well on legacy processors. As a result, their solution is able to accelerate their training of these models to a high degree of accuracy, as summarized by a lead researcher at OMI, Dr. Zhang. We benchmarked with a wide range of interesting state-of-the-art networks, and we see the IPUs are at least multiple times faster than the common GPUs. To give a number, I think it would be at least 10 times faster. And here we have another example in the finance industry, but this time using computer vision models. Tractable uses AI for accident and natural disaster recovery. The processing pipeline uses several techniques. For example, EfficientNet-based models are used to process images, which feeds an attention-based model. They have evaluated GraphCore against their current training regime and saw a 5 times speed gain. This means an experiment that takes a week to run now takes a day. So researchers can potentially run 5 times more experiments, and the company can accelerate the whole research process. Shifting attention to the healthcare industry, here is a summary of some work by Microsoft on chest X-ray diagnosis for COVID-19 using the EfficientNet model. The Microsoft researchers were able to easily port the model to the IPU with the popular tools, and out of the box found a 12 times gain in throughput versus GPU and faster time to train. And the IPU is being used across many areas of research in industries and academic institutions around the world. Here we see some examples of published research papers and press articles. For example, the University of Bristol benefited from the IPU's highly parallel compute in their research on CERN's Large Hadron Collider experiment, with 5.4 times faster performance for their GAN-based application. In another example, research at the Université de Paris has published a paper about the use of GraphCore IPUs to accelerate neural network training for cosmology applications. And now let's take a brief look at the performance of the IPU. We publish performance benchmark results for a number of AI models, and these are available on our website. We were also pleased to make GraphCore's first ever training submission to MLPerf, the AI industry's most widely recognized comparative benchmarking process. Benchmark comparisons show how commercially available GraphCore systems stack up against the latest from NVIDIA. In the chart on the left, we show how the IPU Pod 16 platform compares with NVIDIA's flagship DGX A100 platform in terms of MLPerf ResNet 50 performance, normalized by list pricing. By comparing on this important performance per dollar metric, which provides a good indicator of TCO advantage, we see the IPU Pod 16 platform delivering 1.6 times advantage over the GPU platform on the ResNet 50 model. This advantage for the IPU increases for more efficient next-generation models like EfficientNet, which are more suited to the architecture of the IPU. In the chart on the right, we make the same performance per dollar platform comparison for published results for EfficientNet B4, and here we see the IPU advantage increases to almost 4 times. Perhaps the most important piece of the entire solution is the IPU software stack. The popular stack and graph toolchains provide interfaces to all industry-standard key machine learning frameworks, such as PyTorch and TensorFlow. At the other end, it provides drivers and transport through the hardware. This enables data scientists and machine learning engineers to easily write and run models on the IPU. We support OpenBMC, which provides industry-standard hardware management to Redfish. We also provide runtime visibility into the platform through third-party tools such as Grafana. Industry standard interfaces to orchestration tools and resource managers such as Slurm and Kubernetes are of course provided. Finally, we also provide a full set of our own IPU profiling tools, collectively known as PopVision, for analysis and optimization of model implementations being run on the IPUs. Over the next few years, a substantial fraction of data center compute will be machine intelligence compute. It is therefore naturally anticipated that machine intelligence compute will become the fourth pillar of the data center, along with regular enterprise compute, storage, and networking. This means that machine intelligence compute needs to seamlessly fit into the modern software-defined data center. The software-defined data center is a fundamental change in the industry, so we built the IPU pod with this in mind, and we provide industry-standard interfaces and protocols with open source and open APIs. This means you can incorporate the IPU pod technology into your existing server, storage, and networking infrastructure. Another key benefit of our architecture is the disaggregated scalable AI compute, whereby the regular host server compute is separated or disaggregated from the AI compute. This makes it possible to change the ratio of AI compute to regular compute. As an example, natural language processing workloads such as BERT, for example, require a very different ratio of AI compute to host server compute than computer vision models, which require much more host server pre-processing of the images. To summarize, the IPU and IPU pod systems with our Poplar software are our solution for scale-out AI compute. The integrated networking and scalable architecture enables you to start small and go very big. I hope this has provided a helpful introduction to GraphCore technology. Thank you very much for taking the time to listen to this presentation. We have a lot more information on our website. Feel free to contact us via our website or email address, or follow us on Twitter and LinkedIn.